Now we'll look at an example of solving a linear system of equations. In this case, in this example, we have three equations and we have three unknowns, x, y, and z. Now for this example, I'll tell you beforehand, there is a unique solution to this, so only one combination of x, y, and z that will satisfy all three equations, and there's exactly one that does that. In general, we can't make this assumption, and we would want to test that beforehand before we go and jump in and say that there definitely is a solution to it, and we'll get to that in a future example. But what we want to do is put this into matrix form so that we can use MATLAB's commands in order to solve for the x, y, and z that makes these equations true. So we want to put this into the form of ax equals b. So take it from three scalar equations into one matrix equation. In general, the first step we want to do is make sure that the variable terms are on the left-hand side and the constant terms are on the right-hand side. So if we look at all three of the equations here, on the left-hand side of each of them we have x, y, and z with their proper coefficients, and that's true for all three of them. And if we look at the right-hand side, we have just the constant term, a 10, a 5, and a -3. The right-hand side of no equation contains a variable, and the left-hand side contains no constant, or at least no constant by itself. The coefficients in front of the x, y, z terms, those are okay, but there's no constant term alone on the left-hand side. So the work is already done for us here. It's in the proper format that we're going to want before we take this into matrix form. So what we want to make is this A matrix, the matrix of constant coefficients. So this is what the A matrix would be for this system of equations. And kind of analyze it and break it down. What is going to happen, let me also show you the X here, is that for this matrix A, each row corresponds to one of the equations that are written above. And then each column corresponds to x, y, or z. In this case, I chose the order to be x meaning it's the first column, y meaning the second column, and z meaning the third column. Now if I decide to go with a different order, then the order of the columns of A would be different, and I want to make sure that I'm just aware of which column represents which. And if I look at the way that I'm writing this x column vector, it's in that same order. X is at the top, meaning the first column, y is in the middle, the second column, and z is last, and that's going to correspond again to that third column. If you haven't had linear algebra yet, again, that's okay, but just make sure that you're aware of the order that you're assigning these variables. So looking at the first row of A, if I look at my first equation, I have a coefficient in 3 in front of x, a coefficient of 2 in front of y, and a coefficient of -1 in front of z. Hence, that's why the first row of A is 3, 2, -1. Looking at the second row of A, that's the second equation that I have written above. I have a -1 in front of x. I don't have a y term in the second equation, so I put a 0 in its place, and I have a 2 as the coefficient in front of z. And the third row, I have 1, -1, -1, again, the coefficients in front of x, y, and z respectively. To have the solvable system, again, A must be square, but in general we will look at cases where A is not a square matrix, but we won't get a unique solution to our problem. All right, we have that A matrix. We've designated what our vector of unknown quantities is, in this case x, y, z in that order. So the last thing is we need that right-hand side, we need that column vector of B. In this case, B again is just going to be the constants on the right-hand side in the same order as the system is for matrix A. So we see that first equation at the top, I have 3, 2, -1 as the first row of A. So then in B, I have 10. For the second equation, which is the second row of A, that means that the second row of B has to be the constant 5. And then the third row of A corresponding to the third equation, that means that I put a -3 in for B. Now I can use this information, especially A and B, to solve for that unknown vector x, which contains the variables x, y, and z. Taking this into MATLAB now, I want to enter my matrix A, which we determined was 3, 2, -1, -1, 0, 2, 1, -1, -1. And I need that column vector B, which is going to be 10, 5, -3. And the dimensions of these are important, so you want to keep that in mind. So let's test this. If I have A, that's my square matrix, and B, because I put that transpose up there, in B I have it in the same order, column vector 10, 5, negative 3. As I've said before, this is a 3 by 3 matrix. We could solve this by hand using substitution or elimination, but for the bigger systems we're not going to be able to. But if we did want to just check our answer by doing it manually, we could do that too. I'm going to use the 3 methods that I talked about, but emphasizing the third method to solve for what that unknown coefficient, what the unknown values of x, y, and z must be to satisfy these equalities. So the first method we can use is right from linear algebra. We can take the inverse of matrix A and multiply it by the column vector B. So first, let me just see what the inverse of A is. Right, so if we were doing the inverse of A by hand, it's a pretty time-consuming process, even for only a 3 by 3 matrix. But using inv in MATLAB will take the inverse for us. So this is one way that's going to give us the solution for the values of x that make this true. And we run this whole thing, and those are the values of x, column vector x, that make this true, which means the way we interpret this is referring back to kind of the mapping that we made before. That first value is what the variable x must be, the scalar value x. The second value, 2.1429, is the value that y must be, and 4.1429 is the value that z must be, and this is the only combination of x, y, z that will satisfy all 3 of these equations at the same time. So we do find a unique solution to solve this. Now we're going to get the same answer if we do put in reduced row echelon form the matrix A augmented with column vector B. Let me run just this. Now this presents our answers a little bit differently here. So we see that it took that, I'll show you what this raw part is. We have this 3 by 4 matrix. We give it the RREF command, and I'll run that part again. And what we get is the identity matrix. If we have a unique solution, we have a 3 by 3 identity matrix, but really what we're concerned about is this last column, those values of x, y, and z that make this true. And we see here that we get the same results whether we put it into reduced row echelon form, or if we took the inverse of A times B, that this fourth column is the same as this when we take inverse A times B. And when we have unique solutions, those will always give us the same answers. And then lastly, really the way that I would emphasize is we can use that backslash operator. It's the coefficient matrix, backslash, and then the column vector. So let me clear the screen here just so we can see this. So if I run just line 16, again I get that same unique answer as I got with the 2 previous methods, because that is the only one unique solution that solves this problem. Now something to look at here is I want to just compare how long it takes to run each of these operations. So I'm going to put some ticks and talks in here so I can do some timing of these different approaches. And this is where the methods are really going to be different. Even though we get the same solutions, the time it takes for MATLAB to run them is going to be different. And I'm going to suppress these outputs here so I have a fair comparison in what I'm doing. So now if I rerun this, I'll rewrite a couple times just so we can get kind of an average here. Alright, so the one thing to notice is that the first method and the third method, sometimes they take, I'll say roughly the same amount of time, but certainly the same magnitude of time to, in this case, run the inverse of A times B and to do the A backslash B. So they're both the same order of magnitude in the amount of time it takes. And as I rerun it, sometimes the third method is, the backslash method is faster, sometimes the inverse method is faster. But most importantly, that reduced row echelon form takes much, much more time. Now here we're only talking about 0.02 seconds for this system, which is only a 3 by 3 system. But we see by order of magnitude, it takes 1, 2, 3 orders of magnitude, about 1,000 times as long to run the RREF mode rather than using the backslash or the inverse. For this small system, it really doesn't seem like much of a difference in running these. But let's see what happens if we run a larger system. So for the moment, I'm just going to comment these out and we'll come back to those. So let me look at a 100 by 100 system. And I'll just use random numbers for now, just to demonstrate how the size comes into play in how long it takes. Right, so A is 100 random elements by 100 random elements, and B is going to be 100 elements, also random, and it's going to be a column vector. Right, so we're comparing the 3 by 3 that we just looked at that took basically 0 time to a 100 by 100 system, 100 unknowns, and 100 equations. And now we're going to start to see an appreciable difference between the methods. Right, so we see here, if we use the inverse and if we use the backslash operator, actually even here they take about the same amount of time to run, but the reduced row echelon form takes much, much longer. If I increase it, let's do a 300 unknown by 300 unknown system, so certainly one we would not want to do by hand, and we run this in the 3 different methods for finding our answer. We're going to find a pretty big difference here in the approaches. So for this large system here, by the first approach it took 0.01 seconds. Using reduced row echelon form, it took about 3 orders of magnitude more time than using the inverse, so it took 4.7 seconds using reduced row echelon form. And now using the backslash operator, we see that that took the least amount of time. That took 1 order of magnitude less than using the inverse method. And we see that the larger these systems get, that backslash operator is going to become more and more efficient, much more quick to use, rather than trying to use the inverse or the reduced row echelon form. But again, when we have a unique solution, they do always give us the same answers. So the only difference in this case is how long it takes to run.